Okay, so last time we showed a lot of pretty pictures of different antennas and talked about some of their pros and cons, different types of antennas. And now today, in this last half of the notes, we'll kind of look at some of the mathematical features of the antennas and the properties of the radiation patterns and very important characteristics such as directivity and gain. And that'll lead to some examples of working practical wireless communication link budgets. Okay. All right. Okay, so as it says here, let's start by considering what the radiation from an antenna looks like. Okay, now this could be any antenna. I'm showing some kind of a wire antenna, but it could be anything. Okay, and it's radiating out in space, so it's got a pointing vector. And here's the blue dot, which is where you are, the observer, the observation point. Of course, we could say X, Y, Z, but it's better to say in spherical R theta phi. Now remember, in spherical, R is the distance from the origin. Okay, the antenna doesn't necessarily have to be at the origin, but it's convenient to often put it there. Theta, remember, is the angle from the z-axis going down, so it goes from 0 to pi. And then phi is what's called the azimuth angle. It's the angle going around like this in the horizontal plane. Phi equals 0 on the x-axis, then 90 on the y-axis, and then back to 360 on the x-axis. Okay, so that's the R theta phi. The R vector just means, the position vector. You can call it unit vector X plus unit vector Y plus unit vector ZZ, but it's just where you are in space. And in spherical coordinates, the position vector, R vector, is again described by R theta phi. Okay, all right, so hopefully the picture is clear there. And you see the pointing vector going out in all directions from the antenna, but not necessarily equally in all directions. Now, every antenna has something called a far field. The far field simply means you've gone far enough away from the antenna that the shape of the pattern has sort of stabilized. When you're really close to the antenna, things might be kind of changing as you go out from it, but when you get far enough away, R gets big enough, the shape of the pattern kind of stabilizes out, and that's what we call the far field. Now, let me be a little bit more quantitative about it. So here's the E radiated from an antenna, the E vector. Again, it's a function of R theta and phi. And now here's the claim. If you get really far away from any antenna, mathematically, the E vector always is going to look like this. Now notice there's what I call a spherical wave term that's been factored out. Let's see if this makes sense. Now, we all know about a plane wave going in the Z direction, right? If I had a plane wave in air going in the Z direction, there'd be a term e to the minus j k0z, right? We know that. Now, far enough away from the antenna, really far away, see, this radiation is like a spherical wavefront. But when the sphere gets bigger and bigger, a sphere locally kind of looks like a plane, right? The radius of curvature is so big. So if this radius R gets really, really big, an observer is going to think they see a plane wave coming out there. So notice that in the far field, it makes sense to have a term e to the minus j k0r. It's kind of like Z, but R is really any direction you're observing. This way, this way, this way, this way, right? It's going out in all directions. Now, hopefully this 1 over R makes sense too, because the area of a sphere is, of course, 4 pi r squared, right? And if this antenna is pumping out a certain amount of power, the magnitude of the pointing vector in watts per square meter has to vary like 1 over R squared. And the pointing vector is proportional to the square of the E field, because E is related to H, right, by eta. So the bottom line is, for any antenna, the magnitude of the E vector far enough away has to look like 1 over R. And hence the power like 1 over R squared. So for any antenna, if you go far enough away, you're going to have this term out in front that looks like e to the minus j k0r over R. And that's what I'm calling the spherical wave term. We know it's there for any antenna. We can sort of ignore it. And it's multiplied by something that I'm going to call the far field pattern shape function. F, capital F, reminds us that we're out in the far field now. We know that's got this factor when we're in the far field. This term that's left, E far field, is only a function of theta and phi in spherical coordinates. So it gives us the two-dimensional shape function, the two-dimensional shape of the pattern. If you want to put R back in and have R theta phi, you just multiply by this, right? But see, in the far field, the shape of the pattern doesn't depend on R. It's only dependent on theta and phi. The shape of the pattern has stabilized out. That make sense? So that's what we call the far field. All right, and that's what I'm saying in these bullets here. Okay, so we know every antenna has a spherical term. We're going to sort of just kind of, it always tags along, but this is the important thing, the far field shape function. Now, how far do we have to go away from an antenna before the shape of the pattern has stabilized out and we can say the E field looks like this? Again, this is what we mean by being in the far field. The E field looks like this. Now, this is what I call the Balanis book. It's probably the most well-known antenna book, and it's what we use here for the antenna engineering course that Dr. Long teaches. And almost every university around the country probably uses it. Okay, it's the most well-known antenna engineering book. Anyway, if you want to see a derivation, go consult the Balanis book. But here's a rough rule of thumb. If the distance r from the antenna is greater than 2d squared over lambda, then it's safe to say you're in the far field and the E field is going to look like this. Spherical wave term times a two-dimensional shape function. Now in this equation, D is the diameter of a sphere, like the minimum sphere that encloses the antenna. See this, right? Now, for a practical antenna, I mean, if I give you the frequency and you calculate lambda, and I give you the size of the antenna, you can calculate this. But for most antennas and most typical frequencies, this is not terribly big. You know, it might be 10 feet or who knows, you know, 30 feet or something. So for most wireless communication systems, where the distance between the transmit antenna and receive antenna is a mile or a kilometer or who knows what, you're definitely way out in the far field, right? So for most practical systems, you're definitely in the far field and this equation holds, okay? Now, we talked about polarization of plane waves. Now, this relates to that. Now, remember, it's really a spherical wave coming out of the antenna like this. But again, in every direction theta phi, locally, the observer thinks it looks like a plane wave, right? So just again, you imagine your observer here, you see this plane wave rushing past you in the r direction, and it looks like a plane wave. So if you remember our discussion about plane waves, there's two fundamental polarizations, what we call TMZ and TEZ. Here's a picture of them again. So TMZ means E is in the theta direction, and TEZ means E is in the phi direction or negative phi direction. Okay, now notice I've drawn the picture so that for both cases, if you visualize taking E cross H to get the pointing vector, which is really 1/2 E cross H conjugate, but anyway, visualize taking E cross H, you can see it's going in the positive r hat direction. Again, carrying power radially out in all directions like this, right? Hopefully you agree. Just do it, take a second and do it. Take E cross H here, take E cross H here, and convince yourself that the pointing vector is going out in the positive r hat direction. You see that? You see that? Okay, all right. So that's what they actually look like. Now, depending on the type of antenna, the antenna can radiate TMZ or TEZ or both. The antenna might be radiating circular polarization in a certain direction. And what would that mean? That would mean it radiates equal amplitude TM and TE, but 90 degrees out of phase, right? So it really all depends on the antenna. Now, if you take a simple vertical wire antenna, it turns out that that just radiates only the TMZ polarization. So out in the far field, it's going to have only E theta. But every antenna could be different. So the polarization depends on the antenna, okay? Now, let me do a calculation of what the pointing vector is in the far field. It's similar, if not identical, to what we've done in the past, but let's go through it one more time. Here is the complex pointing vector, 1/2 E cross H conjugate. I'm going to take E and H and express them in spherical coordinates. Okay, thank you. Now, notice one thing here. When I write E and H in spherical coordinates, and it looks like there's a typo here because I forgot the conjugate on H here. Sorry. Okay, pretend you see a conjugate there, okay? All right, but so here's the E vector, here's the H vector. Now notice one thing is missing. See if this makes sense. When I write down the equation for E and H in spherical, notice I'm not putting any r hat component. Does that make sense? Okay, look at this picture. Does it make sense why there's no r hat component? It's like a plane wave. If a plane wave is going in the z direction, you're not going to have any z component, right? The E vector and the H vector stay in the xy plane. We know that, right? So just think of going in spherical. Now z is like what we call the r direction. So in the far field, at least, and I'm not claiming this is true very close to the antenna, But in general, in the far field, you're never going to have any R component of either E or H. Okay? All right. Now, anyway, do the cross product. There's two terms that survive because, of course, theta cross theta is 0 and phi cross phi is 0. So theta hat cross phi hat is positive R hat. So you get E theta. And again, there's supposed to be a conjugate here. So H phi conjugate. And then phi hat cross theta hat is minus R hat. Okay, so you get a minus sign here. And then notice that E and H are related by eta. E theta over H phi is equal to eta. Excuse me, sorry about that. And E phi over H theta is minus eta. Now, why the minus sign here? Okay, again, look, okay, see, if E is in the theta direction here, H in the positive theta direction, H is in the positive phi direction. You see, if H is in the positive theta direction, E is in the negative phi direction, right? Because remember, I want the pointing vector to go out. So that's where the negative sign comes from. So it's negative E phi over H theta, which is equal to eta. Anyway, so you take these two equations here, and then you can use these to solve for H phi and H theta and plug back into here and here for the H phi and H theta. That's what I did right here. Okay, now notice there's a minus sign here, but when you solve for H theta, you pick up another minus sign, so they both cancel. And of course, anything times its conjugate is the magnitude squared. So we have like this. So in the far field of any antenna, the pointing vector is purely in the radial R hat direction, and it looks like this. Okay. Now in air, eta 0 is a real number. It's about 377 ohms, right? So notice in the far field, the pointing vector is purely real. Just like a plane wave going in the Z direction. We already talked about that, same thing. So out in the far field, there's only watts per square meter flowing. There's no VARs flowing far away from any antenna. Okay. Now, another way of writing this term in parentheses is to say the magnitude of the complex E vector squared. You might recall, how do you take the magnitude of a complex vector? Okay, let me remind you, the magnitude of a complex vector squared is vector dot itself conjugate. So you take the E vector here and imagine dotting with itself conjugate. You'll just get basically E theta times E theta conjugate plus E phi times E phi conjugate. In other words, you get this right here. So this thing means the same thing as this. Okay, this is a more compact way of writing it. All right, so there's the pointing vector of any antenna in the far field. Very simple, based on the E field, and again, only watts per square meter. Now, again, in the far field, here is what the E field from any antenna looks like. The spherical wave term times this 2D far field shape function or pattern function. Okay. All right. Now, when antenna engineers plot a far field pattern, they often like to express it in dB and plot it on a polar chart, as you'll have the opportunity to do in that one particular problem on homework 11. Okay, but anyway, so that's called making a polar plot in dB. Now, here's how we do it. So I'll call it dB. Okay, so you take, now again, let's ignore the spherical wave term. We're only focusing on the shape of the far field pattern. So it's just this thing that's important, this two-dimensional function. We take the magnitude of it. Okay. If it's not already real, take the magnitude of it. And we take the magnitude of it, and then we normalize it by dividing the value of it at where the peak of the beam is, the maximum radiation. So this antenna is, spewing out power in all directions, theta phi, but not equally, right? So there'll be some direction called maximum. M star stands for maximum. There'll be a theta and a phi angle in spherical coordinates where you get maximum radiation from the antenna. In other words, this term here is as big as it's ever going to get. So you divide by that to normalize it. Now, when you normalize it like that, this term in this big parentheses here, of course, is always less than or equal to 1, right? Because you divide it by the maximum. When you're at the maximum, this term in parentheses is 1, right? And then away from the maximum, it's always less than 1. Now, of course, now to put in dB, we take 20 log 10. 20, not 10, because it's field, not power, right? Although if you want to talk about power, I could say E squared here and here, and then say 10, but it's the same thing. Okay, but anyway, I'll just say ratio of the E fields and 20. Now, anyway, so if I'm at the maximum, theta equals theta M, phi equals phi M, then this whole thing is 1, log of 1 is 0. So notice that under this normalization, we always have 0 dB at the maximum. So the dB is always negative, and it's always 0 at the maximum. Okay? Now, here's what a typical polar plot looks like. Here's how antenna engineers like to make their patterns. So now, of course, it's a two-dimensional function of theta and phi, but the most common way to do a polar plot is to make one of two types of patterns. One is called the elevation cut or elevation pattern, and the one is called the azimuth cut or the azimuth pattern. Okay? Now, when an antenna engineer says elevation, what they mean is they're changing angle theta. When they say azimuth, they mean they're changing angle phi. And phi is the angle going around like this. So an elevation pattern or an elevation cut means that you're keeping angle phi fixed and you're just changing theta. So phi is fixed and you're just changing theta. Here's theta equals 0. Here's theta equal 90. Let's just use this as an example. I don't know what antenna this really is, just a hypothetical sketch, but just pretending this is the antenna. Anyway, but the z-axis is, let's say, going up. So this is theta equals 0. That's here, right, on this polar plot. And theta equal 90 means horizontal here. So that's here on the polar plot, right? And then theta going all the way down to the negative z-axis is pi. So that's all the way down here on this polar plot. Okay? So on the polar graph, if it's an elevation cut, I pick an angle phi and hold it fixed. Now, if I'm really doing this type of antenna, this vertical wire antenna, that as I'm saying right here, you know, the vertical wire antenna is a totally symmetric antenna. So the pattern is not going to be a function of phi. Any phi is going to be the same. So that's why I said phi equals arbitrary phi 0. Doesn't matter what it is. You can call it 0 if you want, which means you're in the XZ plane, but it's really arbitrary. Now, that's just this type of antenna. For a lot of antennas, of course, the pattern really will be a function of both theta and phi, right? But for this one here, it's only a function of theta. So in the elevation cut, I really don't care what phi is. I'm just going to call it 0, but it's arbitrary. Okay? Now, so remember, it's always 0 dB at the maximum. So you always want to label 0 dB on your outer circle of your polar plot. See that? 0 dB. And then you pick how many dB per divisions you want, and then how many divisions you want going down to the origin. So notice in this one, it's a plot where we have 10 dB per division. Okay, 0 dB on the outside, right? And then the next circle is minus 10 dB, then minus 20, minus 30, right? Now, what is it at the center? Okay, here it's 0, minus 10, minus 20, minus 30, minus 40, minus 50, minus 60 dB. So this is a chart going from 0 to minus 60 dB. Okay? All right, I think on the homework problem it said do something different, but anyway, you get the idea, right? Now, notice on a polar plot, on a dB polar plot, you can never, of course, show an exact null in the pattern. I mean, if you have an angle theta where the far field is 0, what would that be in dB? So if this is 0 here in the numerator, you know, log 10 of 0, what would that be in dB? Huh? 20? Okay, well, it's a reasonable guess, but no. So what's log of 0? Yeah, I guess a mathematician might say that, undefined. But okay, let's be more precise. Let's just say you have a really small number, and it's getting smaller and smaller and smaller. What's the log tending to? Okay, you're on the right track. Go ahead. Negative infinity, right? So now the advantage of plotting on dB is you can show a wide range of values. That's why we like it. I mean, 0 dB down to, in this case, minus 60 dB, right? So a huge range, okay? But the disadvantage is you can never plot exactly where the pattern goes to 0, right? Okay, so the lowest you can get on this particular one is minus 60 dB. Anything lower than minus 60 dB got sucked into the center of the chart, right? And can't be shown. Okay, but that's a small price to pay. But antenna engineers usually like to plot this way. Okay. All right, does that make sense? You'll have to do one in the homework. So does that make sense? Okay. Now remember, another way to do it is to make an azimuth pattern or azimuth cut where I will keep theta fixed and plot versus phi. But I believe in the homework you're doing the same as I'm doing right here, an elevation pattern, elevation cut. Okay. Okay, now we already derived this a minute ago. Here's the Poynting vector in the far field. Now, the total power radiated by any antenna would come by integrating the R component of the pointing vector. There is only an R component, right? I mean, remember, the power going out to any surface is pointing vector dot normal integrated over the surface, right? It's a big sphere, outward normal is R hat, right? So pointing vector dot R hat integrated over this big sphere, radius R. And here's, of course, the usual differential ds and spherical that I'm sure you're familiar with from calculus, right? ds and spherical. Now, so s dot R hat means everything here. Get rid of the R hat. It's all this right here. Now, notice when I plug in right into here, I guess it's pretty obvious, but notice this R squared here cancels this R squared. So you just end up with this. Okay. And pulling out the 1 over 2 eta, I guess this is about as far as you can take it in general. So here's the power radiated in watts from any antenna based on this 2D pattern far field function, as we call it. Okay. Now, I'll use that in a minute. Now, let me come to a really first important definition, the directivity of an antenna. Okay. Now, it could be a function of theta and phi because the antenna is radiating differently in all different directions. So we can say the directivity at any function theta and phi. Oftentimes, though, in practice, theta and phi are chosen to be the direction where the antenna has the maximum radiation. And so normally D means the directivity in the direction of maximum radiation. But technically speaking, it could be in any direction, okay? Now here's the official definition. Remember, this is the definition symbol. The official definition of directivity in some direction is the pointing vector. Remember, the pointing vector only has an R component. Pointing vector in the far field is a function of theta and phi divided by the total power in watts radiated by the antenna divided by 4 pi R squared, where R is just this big radius, of the sphere. In other words, go back to this picture right here, like this. So you're looking at the pointing vector at some point in some direction, theta phi, like right here where the blue dot is. That's the numerator. And then you're dividing by the total power radiated divided by the area of the sphere, 4 pi R squared. Now, let me see why that's a nice definition. Let's see if this makes sense. Now, the antenna is radiating a certain amount of power. It could be 1 watt or 10 watts or something like that. It's radiating a certain amount of power. Now, let's just pretend hypothetically for a second that the antenna radiated its power equally in all directions. No antenna really does that, but just pretend it did. If it did, then what would the watts per square meter be out in the far field? It'd be the power radiated divided by the area of the sphere, 4 pi R squared, right? So the denominator is how much watts per square meter you're going to get in the far field if it hypothetically radiated equally in all directions, right? Now, the numerator is how much watts per square meter you really get in that direction. So the directivity is how much watts per square meter you're getting in a certain direction relative to what you would have gotten in that direction if it radiated equally in all directions. Okay? Now, the more focused the antenna radiates in one particular direction, the higher this directivity is going to be. Okay? If an antenna hypothetically really radiated equally in all directions, well, okay, I'll ask it as a question. If an antenna hypothetically radiated equally in all directions, what would its directivity be? 1, R 0 dB, right? But if the directivity is something like 100 or 1,000, it's a really focused beam. Okay? Now, so that's the directivity, and this is just saying what I just said in words. And sometimes we call this directivity with respect to an isotropic radiator, because again, that's what this is. The denominator is the power density of a hypothetical isotropic radiator. Isotropic simply means radiating equally in all directions. Okay? Now, putting in dB, it'd be 10 log 10 of the actual directivity. Now, 10 here, not 20, because this is not a ratio of E fields. This is a ratio of powers, right? So 10 log 10. So that's directivity with respect to an isotropic radiator. And it's one of the most important measures that we have in antennas. Okay? Here it is one more time. Now, using the equations that I had from a few minutes ago, we can actually come up with a formula for the directivity in terms of the far field pattern, two-dimensional shape function. It's pretty easy to derive. Okay, here's the formula from a few minutes ago for the pointing vector out in the far field. Okay. And just derived a second ago, here's that formula for the power radiated right here. Okay, so that's this again. So that'll go right here in the denominator. And then the Poynting vector will go right here in the numerator. And then just simplify a little bit. For example, if you put this in the numerator, you can see it's going to have a 1 over r squared. And then there's a 1 over r squared downstairs. So the r squareds cancel. And this 4 pi can come upstairs. So just a tiny bit of simplification. And here's the final answer. So if you know this two-dimensional function called the far field shape function, then you can go and evaluate the directivity in any direction you want. Now, you have to do this numerical integration. And for some antennas, you can do that in closed form. For most antennas, you probably have to go to MATLAB or something and just numerically integrate that. Okay, but at least in principle, you can do that denominator integration, and then you can have the directivity. And again, let me remind you, directivity could be in any direction, but the most common direction is whatever theta and phi gives you the direction of maximum radiation. Okay. All right. So here's some pictures just to get the point across. So here's an antenna with a so-called moderate directivity, which could be our good old vertical dipole. Now remember, a resonant dipole is half a wavelength long, remember? And the impedance then is about 73 ohms, most commonly fed with a twin lead. In fact, like I mentioned the other day, you can think of a twin lead just unfolded like that to make the dipole, right? So it's a natural thing to feed it with a twin lead. Anyway, here's a pattern. I'm not going to claim it's drawn exactly 100% accurately to scale, but more or less what it looks like. Okay, so it's not particularly directive. Now it has a null at theta equals 0 or theta equal pi. Okay, and so it won't radiate at all in the far field going straight up. It really has a null in that direction. Of course, you can't show a null; it gets sucked down into the center of the chart, right? But it doesn't radiate all in that direction. You can see the good old vertical dipole radiates the strongest right at theta equal pi over 2, right along the ground, assuming there's ground here. If there's over the Earth, for example, right? And that's it's a good antenna for wireless communications. If you're trying to communicate with a user on the ground, you want maximum radiation in the direction of the ground. Here's a user over here in the far field somewhere. And not only that, but another advantage is it's omnidirectional in phi. So if you're communicating with some mobile user in a car or something, they're driving around, you want omnidirectionality, right? So it's a good antenna for that. But on the other hand, the disadvantage is it's not very directive. Okay, it's not an isotropic radiator. It doesn't have a directivity of 1. It has a directivity of about 1.6, but that's not terribly exciting. Now, if you have something like a big horn antenna or a big dish antenna, that's when you get a narrow focus beam. That's when you get a high directivity, right? Okay. Okay. Now, I'm not going to prove this. You have to plug into MATLAB and do that integral and everything. But anyway, turns out that for the good old resonant half-wave dipole, the directivity is 1.643. Okay, from numerical MATLAB calculation. And here is the pattern function again. Again, maximum angle of radiation, theta maximum is pi over 2 or 90 degrees, straight horizontal. So now when I use the symbol D and I don't put theta or phi as an argument, then it's usually understood to be maximum directivity. So that means theta is pi over 2. And well, I don't care about phi because it's omnidirectional, right? So I just put phi 0 there, whatever, it doesn't matter what it is. Okay, so in the direction of 90 degrees, maximum directivity, D, which means D max, is 1.643. Okay, now beam width is something that kind of goes hand in hand with directivity. In a certain sense, they're measuring the same thing, although one is kind of like the inverse of the other. As it says here, the beam width measures directly, either in angles or radians, how narrow the beam is. Okay, and the narrower the beam, the higher the directivity. More focused the energy is in one direction. Okay, and you might see this acronym. This is very common among antenna engineers, HPBW. It stands for half power beam width. You have to have some definition of what you mean by beam width, how you're going to measure it. And usually it's at the -3 dB or half power points. So here's a sketch right here of just some very typical antenna pattern. I don't know what it is, just some typical antenna pattern. And here's what we call the main beam. Now, I'll get to these guys in a later slide, but notice that it's often common that antenna will not only radiate the main beam, which is what you want, unfortunately, it will radiate these other beams, these secondary beams, which are called side lobes. Okay, the side lobes are almost always undesirable, but in real life, antennas often have them. Okay, and I'll get to that in a second. But anyway, right now I'm focused on the beam width. So now remember, if we agree to normalize it, like I just told you, then we're always going to have 0 dB at the maximum, right? So in this particular hypothetical antenna pattern, I've labeled 0 dB at the maximum. I didn't draw the complete polar plot, but here you can see it's 10 dB per division. So here it's minus 10 dB, minus 20, minus 30, minus 40 at the center of the chart, right? Okay. Now, you may recall that if you have half power, that corresponds, as I say right here, half power, that corresponds to being down by minus 3 dB. In other words, go ahead, verify it on your calculator. 10 log 10 of a half is very, very close to the number minus 3. Not exactly, but we just say minus 3. Now, in terms of the field, remember, power is like the square of the field. So you could say the field level is right here is down from the maximum. The magnitude of the E field right here is down from maximum by 0.707, 1 over square root of 2. Power down by a half. And again, that means minus 3 dB. Okay, so we look at, so half power beam width means we go from one half power point to the other one. We look at the 2 3 dB points and look at the angle change between them. And it could be radians or degrees, your choice, but that's the half power beam width. So obviously, the smaller the half power beam width is, the more focused the beam is. And of course, that's going to mean higher directivity, right? So they go hand in hand. Okay, so it's a pretty simple concept. Any questions? Okay. Now, again, we don't normally like these side lobes, but it's reality. We usually get them. So engineers will talk about what the side lobe level of an antenna is. Now, what they're usually referring to is they look at the strongest of the side lobes, because that's the worst case, right? The biggest one, and look at what the dB level is of it, and that's how they classify the side lobe level. So we look at this hypothetical pattern here. So again, it's got, and by the way, notice that it's got a lobe pointing in the backward direction too, 180 degrees opposite from the main beam. You can call that a side lobe. You can also call it a backward beam. But anyway, if we take the biggest of all these side lobes, it's this one right here. I drew a red circle around it. And go to the polar chart here. If you read it off, it looks like, remember, here's minus 10, here's minus 20, right? So it looks like it's at about minus 12 dB, right? So for this antenna, I would say the side lobe level is about minus 12 dB. Now, that's not a particularly good side lobe level, by the way. A good antenna should probably have a side lobe level that's about minus 20 dB, right? And for some applications, depends on what the system requirements are. But for some antennas, the system requirements might be minus 30 dB or sometimes even minus 40 dB if you really can't tolerate hardly any side lobes, right? Now, by the way, how come we don't like side lobes? Well, obviously, one reason is wasted power. Here you're trying to communicate with somebody over here, and that's where you want to focus the energy, right? So energy that gets focused anywhere else is lost power, right? But it could get worse than that, because if power is going in some other directions, it can cause interference and other bad effects. And if this is a receive antenna, then of course, if it's transmitting, it's power wasted in that direction. If this antenna is being used to receive, then that means it's not going to pick up signals coming from this direction, even though you only want to come from this direction, right? So that would enhance the noise level or the interference level that you're picking up, right? Side lobes is going to give you increased noise, right? Coming from, maybe it could even be like in a military system, it could mean that this system is now more susceptible to jamming, because there might be some kind of enemy or something that's sending out a jamming signal, and the side lobe will directly pick up that jamming signal. Okay, so anyway, side lobes in general are bad. So we care about the side lobe level. Okay. All right, any questions on that? Okay. All right. Another very important metric is the radiation efficiency of an antenna. It's very common sense. It's kind of the same definition as efficiency of anything, power out over power in. Anyway, so radiation efficiency for an antenna is defined as power radiated out into space, of course, divided by power being pumped into the antenna. If there's no loss of efficiency, it's 100% efficient, then whatever goes in gets radiated out, right? Now, of course, multiply this by 100 if you want percent, right? Of course. Okay. Now, why is an antenna not 100% efficient? Well, the antenna is made out of real copper, aluminum, and depending on the type of antenna, maybe dielectric loss. Not every, like a wire antenna would not have that, but remember, like a microstrip antenna does, because it's made on a dielectric, a substrate board, right? So a microstrip antenna not only has metal loss, but dielectric loss too, loss tangent to the dielectric. So it's kind of worst of all. Now, a typical wire antenna might have an efficiency of 97, 98%, so it's not a big concern. Typical microstrip antenna might have an efficiency of 80% or 75%, so it's more of a concern. Okay, but every antenna has an efficiency. Okay, now here's perhaps the most important definition we're going to meet in the notes, and it's very important for the examples we're going to be doing later. The gain of the antenna. Now, again, it's a function of the angles that you're observing the transmitted power, although often we think of the angles as being the angles of maximum radiation, but in principle, it could be any direction you want. Now, by definition, the gain is simply the directivity in that direction times the efficiency of the antenna. So it's very simple, just efficiency times directivity. Now, in a minute, I'll show you why we like this definition so much. Okay, but that's the definition of it. Now in dB, 10 log of it, 10 log 10 of it, okay? Now, this slide really explains why we like gain so much. Yeah, go ahead.
Always less than 1?
Gain? Efficiency?
Yeah.
Yeah, well, I mean, because, I mean, you can't radiate more than you're pumping in, of course, right?
Right.
Yeah, so the maximum efficiency you're ever going to get is 1, of course, 100%. Yeah, but in real life, it's always less than 1 or 100% because of losses. Okay, anything else? Okay, so again, it's a fairly simple calculation, but it leads to this formula here, which really explains why we like gain so much. Now, let me remind you the directivity definition. Pointing vector watts per square meter out in the far field divided by what the watts per square meter would be if it hypothetically radiated equally in all directions. Okay. Now, let's just take this equation, this definition of directivity, and first just solve it for the pointing vector by taking this denominator across the equal sign. Okay, very simple. So now this is the watts per square meter in the far field. Okay. And now let me go ahead and do this. I've got power radiated here. And now let me relate it back to this equation here. This is the definition of radiation efficiency. See, I've got power radiated here. Here's the definition of efficiency. It's got power radiated in it, right? So I can take, and if I want to solve for P rad, I'll say P rad is power in times efficiency, right? So that's what I did. Power rad was substituted for efficiency of the antenna times power pumped into the antenna. Okay. And then look what happens. Look what we see. Efficiency of the antenna times directivity, right? Efficiency times directivity, that's what we define to be gain, right? Now you see why we wanted to define gain to be this way, right? So efficiency times directivity is gain. Now, let's give an important physical interpretation of this equation. So when you have power coming out of a transmit antenna, going off in some direction towards a user with the receive antenna, this equation is extremely important because it tells you what's the watts per square meter that's going to be picked up by that user. Okay, so here, let's go over it. The user, the transmitter, the user pumping in power into the transmit antenna pumps in PN. Here's what you do. If you know power going into the input transmit antenna, you first pretend it's going equally in all directions. So divided by the area of the big sphere, 4 pi r squared. Then you multiply by the gain. So the gain tells you how much more watts per square meter that person's going to receive over there relative to what that person would have received if the person with the transmit antenna simply pumped in the power and it went equally in all directions. Okay, now the gain accounts for everything. It accounts for the fact that there's a directivity, so the transmit beam is focused, but it also accounts for efficiency of the transmit antenna, because you know the person with the transmit antenna might be pumping a certain amount of power, but it might be a really lousy antenna and only 10% of the power gets radiated, right? The gain accounts for that too. It accounts for everything, right? The total watts per square meter being picked up by the user, depending upon relative to what would have come out if it went equally in all directions. So you one more time. To get the watts per square meter at the user, you calculate based on all the power being radiated and going equally everywhere, and then you just multiply by the gain. So a very important number for calculating watts per square meter at the user. Okay. All right. Now we'll get back to that when I do these examples. Now, another thing here is that any antenna, now I want to talk a bit more about what happens for a transmit antenna and a receive antenna. Now remember, any antenna can be used both for transmit or receive, but I want to talk about the two different situations. Now, first, antenna being used as a transmit antenna. Now, I think I said this the other day, in fact, but you got a feeding transmission line, whatever it is, a coax or twin lead or something coming in, feeding the antenna. Now, as far as the feeding transmission line is concerned, any antenna just looks like any other load. It's a complex impedance called ZN, the input impedance. Okay. And so it's got a real part RN and a reactance XN. Now, usually, in most cases, I think you can appreciate that you want the antenna to be resonant. And resonance, what we mean by that is the imaginary part, the reactance is zero. So the feeding transmission line sees a pure real load. And then not only that, but normally you want the RN value to be equal to the Z0 of the line, right? And I think by now you can appreciate why we want that, because you want to see a perfect match, right? All the power from the incoming transmission line will get absorbed by the load. Now, what does getting absorbed by the load mean if the load is an antenna? That means it got radiated, right? So all the power got radiated, none of it got reflected back to the transmitter. Okay, that's what you normally want. Now, let me remind you that every antenna can have a different input impedance, but for the resonant half-wave dipole, remember, half-wave, it's resonant, so X is 0, and the real part's about 73, like we talked about. Just keep that in mind for the examples later. Okay, now what about if the antenna is being used to receive? What about that? Okay, now, again, just to draw something, I'm drawing a wire antenna, but it could be any antenna. So here's that field coming out. It's really a spherical wave, but the user is so far away that that user just sees almost like a plane wave coming and hitting their antenna, right? So it's got some E incident coming from the distant transmit antenna, hitting the receive antenna. Here's the actual watts per square meter, if you know the E incident, okay? Now, an antenna, just like anything else in circuit theory, can be modeled with Thevenin equivalent circuit. The concept of Thevenin equivalent circuit is very general, and even though you learned it in circuit class, it applies to any linear system. Okay, so a receive antenna can be modeled with Thevenin equivalent. Here's a Thevenin equivalent for a receive antenna. Okay, now it works the same way in circuits. Okay, so you got a Thevenin voltage. I'm in the phasor domain, so phasor Thevenin voltage. What does that mean physically? Just think about circuits. It means the same thing as open circuit voltage, right? So even though the receive antenna is practically connected to some kind of receiver, in other words, some kind of a load here, if you just disconnect everything, leave it open circuited, the open circuit voltage is the Thevenin voltage. That's what it means, right? Okay, and it's got a Thevenin impedance. Now let's recall how that worked in circuit theory. How do you calculate Thevenin impedance of a circuit? Okay, one way to do it is to deactivate all sources in the circuit, right? And then look in and say, what is the input impedance? It works exactly the same thing with an antenna. But what does it mean now to deactivate sources? It means get rid of this plane wave coming in, right? Okay, so just take the antenna by itself. Don't excite it. Just take the antenna by itself, look in and ask yourself, what is the impedance? But that's what we call the input impedance, right? Like for the wire antenna at resonance, 73 ohms, right? So the Thevenin impedance is the same thing as just input impedance. And again, every antenna could be different, but if this was the good old half wavelength resonant dipole, it's going to be 73 ohms. Okay. Now, once you have the Thevenin equivalent circuit, you can connect it to a load, which is like a practical receiver, calculate the power going to the receiver, do anything you want with it, right? Okay. Now, let me mention how you can get the Thevenin voltage. Okay, one way to do it is to use the concept of effective length. Now, you're not going to be doing this on the homework, and you're going to be using a different concept called effective area, which, to be honest, is my preferred way because it's a more general way. The concept of effective length is something that only applies to one type of antenna, and that's a wire antenna. Okay, wire antennas are very common, but it only applies to that type of antenna. That's why it's not as general as the method I'll show you next, which is the effective area. But nevertheless, let me just briefly mention what this is. That's what I'm saying here. But anyway, so you have an incident E field coming in, striking the antenna. Now, let me remind you that E has units of volts per meter. Okay, here's what you do to get the Thevenin voltage. Now, the wire antenna only responds to the component of the E vector that's parallel to the wire. That's why you take E incident dot unit vector L, which points along the direction of the wire axis. Then you multiply by L effective. Okay, remember, so this is volts per meter. You want to multiply by a length that's units of meters to get the volts. Now, if you're being very naive, you might think, okay, well, if the E field is some volts per meter, I'm just going to multiply by the physical length in meters of the wire. That'll tell me the volts. Well, that's kind of the right thinking, but not exactly right. If you go through the derivation, you'll see that the effective length is not exactly the same thing as the physical length. Okay, I'm not going to drive that or explain it, but let me just say this, just for your information. I'm not going to do anything with it though. But if you have a resonant half-wave dipole where the length is lambda over 2, then it turns out that the effective length is the physical length times 2 over pi. Now, 2 over pi is a number that's not that different than 1. So it's not that wrong to say that the effective length is just the physical length, but that gets it right, okay? So anyway, but let me again emphasize what's in the box here. I recommend the effective area way of calculating power going to a load, not using this effective length, because the effective area is a more general way of doing it. It still applies to wire antennas, but it applies to any type of antenna. Okay, I already mentioned this. So at resonance, the dipole 73 and the monopole is half of it, remember? Anyway, again, the Thevenin equivalent circuit or any receive antenna. Now, let's get to this effective area. This is the last important topic, but it's the most important one of all. Okay, the effective area of an antenna. Now, effective area is a concept that goes along with an antenna being used as a receive antenna. Okay, as a receive antenna. Okay, so here's how it works. Now, I'm not going to derive anything. It's derived in the Balanis book. Okay, so take Dr. Long's book course if you want to see derivations, or read the Balanis book, but I'm just going to explain how it works, okay? Now, first of all, the assumption of the formula is that the antenna has been connected to an optimum load. Now, what does that mean? So here's the Thevenin equivalent circuit of antenna. Now, I'm sure you remember from circuit theory that anything with a Thevenin equivalent circuit like this is going to supply maximum power to a load when the load is chosen to be the optimum value, which is the conjugate of the Thevenin impedance. Remember that from circuit theory? You know that, right? Okay, so let's assume that that's true. That's what this formula assumes, in fact, that the load, which you can call the receiver, that's connected to the antenna, is optimum load, so its value is the complex conjugate of the Thevenin impedance. Now remember, normally you want the antenna to be resonant, so Z Thevenin is real. But anyway, but in case it's not, the conjugate is there. But like as an example, let's say I'm using my resonant half-wave dipole to be a receive antenna. If it's resonant, the impedance is going to be real, input impedance is going to be real, 73 ohms. So that means Z Thevenin is 73. So the optimum load to connect to my receive antenna is going to be 73 ohms. I'm going to get maximum power into my receiver if the receiver is a load of 73 ohms. Okay? Now, that's the assumption for this formula here. Okay? Under that assumption, here's the formula for how to calculate power going into the load. PL means power going into the load. Okay? It's the power density of the incident wave, thinking of this wave as a plane wave hitting the antenna coming from the transmitter, right? Watts per square meter, power density of the incident plane wave hitting the antenna, times something called the effective area of the antenna. Okay, so no matter what the actual real shape or size of the antenna is, just visualize in your mind that the antenna has been placed by this big, like, circular disc. Doesn't really have to be circular, but some kind of circular area, and it's got an area called A effective, and all the watts per square meter that come and hit that area just get absorbed and transferred to the load. That's how you visualize this working, right? So obviously a bigger effective area, that antenna is capturing more power, transferring more power to the load, right? Okay, I'll show you a formula for area effective in a second, but that's how this concept works. Now, if we know the power going to the load, we can go backwards and figure out the magnitude of the V Thevenin. Normally, you don't have to do that. Normally, it's the power going to the load that you really care about, but if you want to go backwards and figure that out, that's just simple circuit theory. Okay, so anyway, now the real important question is, how do we calculate effective area? This is derived in the Balanis book. Okay, so Remember, any antenna has a gain, efficiency times directivity. So when that antenna is being used as a receive antenna, and you want to calculate its effective area, here's the formula. It's the gain of the antenna times wavelength squared over 4 pi. And again, gain means gain in the direction, theta and phi, that the wave is coming in, hitting the antenna. Usually that's always the direction of maximum, though, usually. Okay. All right. Now, this formula assumes that the incoming signal is optimally polarized in the direction the receive antenna is expecting. So, for example, let's assume my transmit antenna was a vertically polarized wire antenna, and my receive antenna is also a resonant half-wave vertical dipole. Okay. Then gain of the receive antenna, this is the transmit, this is the receive. Gain of the receive, it's in the optimum direction, optimum polarization, vertical. So I'm just going to use the gain of 1.643. Okay, that's the directivity, but if it's assumed it's perfectly efficient, directivity is equal to gain, so 1.643. Now, if the transmit antenna starts rotating, then the E coming in is going to be tilted with respect to the receive antenna, and it's going to start picking up less and less signal, less and less power, right? And if there's an angle theta of rotation like this, then there's going to be a term that looks like cosine theta for the voltage picked up, or cosine theta squared for the power delivered, right? So there's a loss in power delivered to the receiver by cosine squared theta. If theta is 90, the White's antenna is not going to pick up anything, right? Okay, but anyway, this formula assumes optimum polarization, okay? Whatever it is. Could even be CP. This could be a transmit CP and a receive CP, but they both are right-handed or both left-handed, right? Optimum, okay. Polarization match between transmit and receive, then this formula applies. Okay, let's do an example to calculate the effective area of a lossless just to keep it simple, resonant half-wave dipole, okay? And I'll assume the wave is coming in the optimum direction. Remember, this thing radiates the best horizontally, theta equal 90 degrees. So I'll assume that's direction. Okay. Now here's the formula. If I use this as a receive antenna, here's the formula for the effective area that I just mentioned from the Balanis book. Now gain is efficiency times directivity, but I'm assuming there's no loss. So gain is equal to directivity. That's probably good enough for a wire antenna. I'm not going to worry about loss in a wire antenna. The efficiency might be 0.99 or something like that. I'm not going to worry about it. Now remember, the directivity in the optimum direction, 90 degrees, is 1.643. And I've got lambda 0 here. But let me remind you that if I say it's a resonant dipole antenna, then lambda and length, L, are related because L is lambda over 2, right? Or I can solve this for lambda 0 here and say lambda 0 is twice L, right? Now, if you just simplify out, this comes out to be roughly 0.5 times L squared. So it's kind of a simple way to think of the effective area of a dipole antenna. 1/2 its length squared. So, you know, if it's got a length L, think of generating a square L by L, okay? And then the effective area is roughly that cut in half, roughly, okay? Now notice, this may or not be obvious to you, but let me make an important point here. For general arbitrary antenna, effective area has nothing to do with the physical area of the antenna. This could be a skinny wire where the wire is, 1 millimeter in diameter, or even less. So if I take the physical area of just the wire itself, well, that might be almost nothing, right? There's nothing to do with the effective area. The effective area is still going to be pretty big, right? It depends on the length of the antenna, okay? So don't confuse physical surface area of the antenna with effective area, okay? All right. Okay, does that example make sense? Okay, all right. By the way, it's interesting side note. Now, remember that any resonant dipole wants to have a length that's lambda over 2. So if I give you different, I showed you pictures of, like monopoles, that could be the big tower, hundreds of feet, a little thing on your cell phone or something, right? It all depends on the frequency. So hope this note makes sense. Look at the formula here. Okay. So am I going to pick up, if I got the same watts per square meter coming in, am I going to pick up more power if I go to lower frequency or higher frequency? Low, because if we go to lower frequency, wavelength gets bigger, so L gets bigger, and therefore effective area gets bigger, right? Right, good, okay. But what's the disadvantage of low frequency? You got bigger, bulkier antennas, right? Higher frequency, antennas become small. Yeah. Well, it wasn't derived, but remember, it came back here. Let's see. Let me show it to you. Right here. Yeah. Okay. Now, let me remind you that this is the formula for directivity of any antenna. So what you have to do is actually take the far field pattern for the dipole, plug it in here and here, and go to MATLAB and integrate this, right? I didn't do any of that. But I'm just saying the result would be 1.643. Okay. Anything else? So we're up to the grand finale, a couple of nice examples. And again, in homework 11, you have a couple of similar ones. Wireless communication example between two dipoles. Resonant dipole used for transmit, resonant dipole, in other words, half-wave dipole used for receive. Okay, now let's look at this system here. Operating at 1 gigahertz, where this is the wavelength, or in other words, 0.29979 meters. You'll, of course, eventually want to convert everything to MKS, right? Okay. Power being pumped in to the transmit antenna is 10 watts. There's a 1 kilometer distance in this wireless link between transmit and receive. Notice 90 degrees on transmit and receive, optimum orientation, both vertical, so optimum, polarization match. Okay. To get maximum power delivered to this load, which is the electronic receiver or whatever, I'm going to assume it's a load. It has a conjugate of the input impedance, the Thevenin impedance, which is 73, right? So therefore, the optimum load here is 73 ohms, and then it's going to pick up the maximum amount of power. I'll also assume that both antennas are lossless. The efficiency is 1 or 100%. So therefore, gain, which is directivity times efficiency, is the same thing as directivity. And notice optimum direction again, optimum polarization, everything. So 1.643. And since they're totally efficient, there's no loss. So whatever power goes in is also power radiated, right? Okay. And the goal is find the amount of power that can be received by this receiver in this system here. Okay. Any questions on the problem? Okay. So power being received by this optimum load, 73 ohms. Remember, optimum match is assumed in these formulas, right? Going to be the power density incident, striking, here it is, striking, the transmit, the receive antenna. We have to calculate that in a second. But the power density incident, watts per square meter, times the effective area of the receive antenna. Okay. So now what's the effective area of this receive dipole antenna? So it's always gain times lambda squared over 4 pi. The receive antenna is said to be 100% efficient, so gain is its directivity, 1.643. So that's going to be plugged in right in here. Now, what about this? The power density incident, watts per square meter, coming from the transmit antenna hitting the receive antenna. What's that? Okay, this is that formula I showed you. It's very important for watts per square meter out of a transmitter, remember a few minutes ago? So power density incident, you say power into the antenna, 10 watts. You pretend it goes equally in all directions over 4 pi r squared, and then multiply by the gain of the transmitter. Remember that formula? So I know the power going in, 10 watts. I know distance r. So that tells me the power density incident, watts per square meter, hitting the receive antenna. Now notice, by coincidence, it's 1.643 in both places, but that's because both transmit and receive antennas were the same, right? And a different problem, there might be 2 different antennas, receive antenna, transmit antenna, right? So that's why I label it, just so you can keep it straight here. Okay, but anyway, so plug in. So effective area, plug in right here. Power density incident from the transmitter, plug in here. And now just plug in all these numbers. Lambda 0, remember, convert to MKS, so 0.29979 meters. Power in was 10 watts pumped into the transmit antenna. R, which was 1 kilometer, which of course you're going to call 1,000 meters, right? So plug all that in, and it comes out to 1.54 times 10 to the minus 8 watts. So that's the amount of power the receive antenna will pick up if it's 1 kilometer away from the transmitter. Okay, it may sound pretty small, but a good receiver can pretty easily receive that. Okay. Any questions? Now, let me make one note about a dish antenna. Same thing applies to a horn antenna, but a dish antenna. Now, the same formula applies that relates effective area to gain. Okay, because that applies to any antenna. But notice that for the dish antenna, we already know the area, right? Okay, see, I used this formula before, like for the dipole, I knew its gain, 1.643, and I wanted to calculate its effective area. For a dish, you go the other way. For a dish, you already know the area. It's the area of this big circular aperture. It's going to collect all the energy that hits it, right? So I already know the area. So now you can go the other way and use it to calculate the gain. Now, there's one caveat, okay? You might think that the effective area is just this physical area of this big circle, and that's not too far from being true, but people like to sneak in something that they call the aperture efficiency. And so they say the effective area is this physical area. If R is the radius, of course, the area, the physical area is pi r squared, of course, right? So it's a physical area times something called the aperture efficiency. Aperture efficiency counts for various losses, various ways. No dish is perfect, including something called spillover loss, which is easiest to explain on transmit. If you have a feed here and it's transmitting, some of the energy just misses the dish and goes off into space. It doesn't get bounced off the dish. That's called spillover loss. Anyway, all losses are counted for in something called aperture efficiency. And it's so the aperture efficiency is less than 100%, but often if it's a good dish, not too far, maybe 75%, maybe 80%, maybe 90%, something like that. Okay. Now, anyway, with all that background, let's work this final example. Dish and CubeSat. Here's the dish, an actual picture of the dish that's been referred to in the example. As part of the NASA Deep Space Network, where they have big dishes in various locations around the world. This is the one at Goldstone, California, which has a diameter of 70 meters. Okay. And we're going to assume it has an aperture efficiency of 0.75 or 75%. I just made that up. I didn't look it up. I don't know exactly what it is, but it's probably a reasonable number. Anyway, so now in this example, NASA is using this dish to communicate with a CubeSat. Remember, I showed you one of those small little satellite type of things, 10 by 10 by 10 centimeters. Anyway, a CubeSat, which is orbiting Mars, and will take a distance of 50 million kilometers between Earth and Mars. And the CubeSat, I showed you a CubeSat before that has like a dipole or monopole on it. It's often very common to put microstrip antennas on CubeSats too. So I'm going to use a microstrip antenna on the CubeSat. I'm going to say the microstrip antenna has a gain of 8 in the direction of maximum radiation. If here's a surface and the microstrip antenna is on it, this will be the direction of maximum radiation perpendicular from the microstrip antenna. Anyway, it's got a gain of 8, which means 9.03 dB. In other words, 10 log 10 of 8 is 9.03. Okay, we'll use the number 8, but I just gave you this anyway, in dB. We're operating at 10 gigahertz. CubeSat is radiating at 10 gigahertz, and the CubeSat is radiating an input power of 1 watt, which is typical that a CubeSat might really be radiating. Okay, anyway, how much power can NASA receive by this huge dish, which has a diameter of 70 meters, assuming it's got an aperture efficiency of 75%? Express your answer in watts and in dBm. I mentioned a month or so ago what dBm is. dBm means dB relative to a milliwatt. So just a reminder, if I know what the received power is, to convert it to dBm, I'll divide by a milliwatt, which is 0.001 watts, and then take 10 log 10 of it. So that's converting watts received power to dBm. Okay, so that's simple once we have the actual power received in watts. All right, so here's the calculation. It's pretty straightforward. So the power received by this big dish. Now remember, let me remind you one more time, all these calculations and formulas assumed an optimum match. I'm assuming this big dish ultimately goes to a match load, right? Optimum match. Okay, anyway. So the power received is power density incident, which is watts per square meter coming from this CubeSat 50 million kilometers away, right? Hitting the dish, and the dish has an effective area called A effective. Now, so since this is a dish antenna, right, I don't need to calculate effective area by going to gain like I did before for the dipole. Remember, I knew the gain was 1.643. I converted that to area effective. Now I already know it's a dish. I already know the effective area. It's the physical area times the aperture efficiency. Now the physical area is just the actual physical area of the circular, dish. So it's pi radius squared, diameter was 70 meters. So cut it in half to get radius, right? So physical area in square meters, that's this. And then multiply by the aperture efficiency, which is 0.75, 75%, so 0.75. So that's how I get the power received, okay? And then I need power density incident hitting the dish from the CubeSat. Go back to that same formula again. Once you know the power going into any transmit antenna, this is the watts per square meter hitting the receive antenna. You imagine all the power pumping in, pretend it goes equally in all directions, divide by 4 pi r squared, and then multiply by the gain of the transmit antenna. So the CubeSat had 1 watt being pumped into it. R is the distance, 50 million kilometers. Okay, convert to MKS in meters. But anyway, 4 pi r squared, gain of the transmit. So that's gain of the CubeSat antenna, not the gain of the dish, right? Gain of the transmit antenna, which was 8 or 9 dB, but don't use dB in this formula, right? So just 8. So you plug all that in, and the power received is really small, but it's 50 million kilometers away, right? It's a CubeSat only radiating with 1 watt. So the dish can pick up about 10 to the minus 19th power watts. Okay, if you convert that to dBm, about minus 151 dBm. So your everyday receiver cannot receive that, but NASA can receive it. Okay, because they have very special cryogenically cooled, very ultra-sensitive receivers, right? And you don't see it, but it's probably in some building somewhere here connected to the dish. And they can actually receive signals that low. Now, because it's such a weak signal, okay, the signal to noise ratio is going to be terrible. Okay, if you've taken communication theory, you know that the communication data rate is related to the signal noise ratio, right? That Shannon formula. So with this kind of a low power, the SNR is going to be terrible, and maybe the bit rate could only be something like, who knows, a few bits per second, right? Maybe, but they can still process data coming from the CubeSat that far away, right? Yeah, go ahead. Well, I don't know who's first, but okay.
I was just going to ask, how do you calculate or how do you convert it to dBm again?
Right here. Yeah, this is watts received. This converts it to dBm. Okay, dBm is unitless because it's watts over watts, 1 milliwatt, but watts over watts and 10 log of it. Yeah, go ahead, please. Okay, well, it's a good question, and actually, this might help answer it. Let me go to this equation here. Now, notice in this calculation for the dish, I didn't need the gain of the dish because I already knew its area, right? For the dipole, I need the gain first. I convert gain into area, right? But now I already knew the gain. I mean, I already knew the area. So I don't need gain of the dish, but nevertheless, I calculate it again because it's related to effective area, right? And now it's the effective area that's known. This thing times this, right? That's the effective area. I didn't actually give a final number for the effective area, but it's just this times this, right? But it's a huge dish. It's going to be a huge area, right? So anyway, if you plug the area into here and calculate and the frequency, lambda, and you calculate the gain of this dish, it's enormous. Okay, 40 million. 40 million. Now remember, wire antenna, 1.643. The gain of this goldstone dish, 40 million. Right? You see why NASA likes to use huge dishes to communicate out in space, right? You need that extremely focused beam to really be able to receive good signals or to transmit. If this thing's being used to transmit a signal to Mars, that beam is really focused right where they need it, right? You convert it to dB, 76 dB, right? Now, it would be hopeless to try to pick up a signal from a CubeSat in Mars down here on Earth with a resonant wire antenna. That would be absolutely hopeless, right? In that case, it wouldn't be minus 151 dBm. It might be something like minus 1,000 dBm. I don't know, whatever, right? It'd be absolutely hopeless. At least this has some hope. Again, the bit rate might be a few bits per second, but they can still do it. Okay. All right, anything else?
Because of that gain being so high.
Absolutely. Yeah, the physical area, well, if it's being used to receive, it's because the effective area is so huge. If it's being used to transmit, then it's because the gain is so high, but they work hand in hand. It's the same thing, right? Same thing. So gain is high, the beam is really focused, it almost looks like a needle, right? And so it's going to put a spot right on that CubeSat when it's transmitting to the CubeSat. On the other hand, when the CubeSat is transmitting, it's receiving, it's got this huge area so it can collect energy effectively, right? Okay, so again, works hand in hand. Big effective area means high gain. Okay, all right, so hopefully you feel comfortable about our time here. Perfect timing, by the way. Hopefully you feel comfortable now doing this kind of a calculation in homework 11, right? Okay, all righty. So any questions before we adjourn for the holidays? Yeah.
So exam two will homework 10, assuming, or
Homework 2, that's all on the web, it's on Blackboard, right? But exam 2, Thursday after Thanksgiving, will cover through homework 9. Homework 6, Smith charts, up through homework 9. Okay, now I already put this note on Blackboard. Let me just remind you, although homework 10 and 11 are not going to be exam 2, they're going to be, quote, strongly emphasized on the final exam. Now, I don't know what that means, but I wouldn't be terribly surprised if as much as 1/3 or maybe even a half of the final is homework 10, 11. So they're going to be really important for the final. Okay. All right. All right. Thank you.
Want to remind you to check, perhaps check your junk email.